Hello, welcome to the NPTEL online certification course on deep learning. We are discussing about the discriminant function and the decision boundary among different classes. So, in the previous class, we have considered two simple cases where the covariance matrices of the different classes they are same, and in one of the case we have assumed that the covariance matrix is of the form sigma square I, where sigma is the variance of all the components of the vectors and I is an unit matrix, which indicates that the covariance matrix is diagonal, all the off diagonal elements are 0 and all the diagonal elements are same, and that is a case of distribution of points where the points are spherically distributed or hyperspherically distributed. And in the second case, we have assumed that sigma or the covariance matrix of all the classes are same, but the covariance matrix need not be of the form sigma square I. That means, I also have off diagonal elements which are non-zero. And this is a case of distribution of points where the vectors are distributed in ellipsoidal fashion or hyper ellipsoidal fashion. So, what we have discussed in the previous class is the decision boundary under various cases of covariance matrices, and we are going to continue with the same discussion in this class with few more examples. So, where we stopped in the previous lecture is we have assumed the case where the covariance matrix sigma I is equal to sigma. That means, the covariance matrix of all the classes are same, but here the covariance matrices need not be diagonal only. And given this case, we have in the previous class computed that g I x or the covariance the discriminant function of the ith class is given by w I transpose x plus w I naught, where we have seen that this w I is of the form sigma inverse mu I, and w I naught was simply given by minus half mu I transpose sigma inverse mu I plus log of p of omega I, where p of omega I is the a priori probability of class omega I. So, given this, again as we have done in the other case, I can compute the decision. So, here you find that because this g I x is of the form w I transpose x plus w I naught, again this discriminant function is a linear function, because I do not have any quadratic term in x in this expression. So, the discriminant function here again is a linear function. So, given such discriminant functions as we have computed in the previous case, I can compute the decision boundary between the two classes omega I and omega j. So, what will be the decision boundary? The decision boundary here again will be given by g x is equal to g I x minus g j x, and because on the boundary g I x and g j x they are equal. So, I will have g I x minus g j x equal to 0. And you find that what was our expression for g I x? G I x was of the form sigma I mu I sigma mu I transpose sigma inverse x minus half mu I transpose sigma inverse mu I plus log of p of omega I. Similarly, when I compute GJX, GJX will be mu J transpose sigma inverse X minus half of mu J transpose sigma inverse mu J plus log of P of omega J. So, if I simply subtract this Gix minus Gjx and equate that to 0, my expression will simply become, when I compute here Gx, which is nothing but Gix minus Gjx equal to 0, that simply becomes mu I transpose sigma inverse minus mu J transpose sigma inverse X of this minus half of mu I transpose sigma inverse mu I minus mu J transpose sigma inverse mu J plus log of P omega I upon P omega J, that will be equal to 0. Okay. And if you simplify in the same way that you have done earlier, you find that this will lead to an equation of the form W transpose x minus x naught, which is equal to 0, where this W in this case will be given by sigma inverse mu I minus mu J, and x naught will be given by half of mu I plus mu J minus 1 upon mu I minus mu J transpose sigma inverse mu I minus mu J. Here it will be log of P omega I upon P omega J into mu I minus mu J. So, what does it indicate? It indicates, as before, that because the equation of the boundary, the decision boundary between the classes omega 1 and omega j is of the form W transpose x minus x naught equal to 0. And if you remember, this form is similar to what we have obtained in the previous case, where the covariance matrix was a diagonal matrix for all the classes. But what is the difference? In the previous case, this W was simply mu I minus mu j. That means, W was the vector drawn from mu I to mu j. But in this case, W is sigma inverse mu I minus mu j. So, which means that W is no longer in the direction of the vector from mu I to mu j, but the direction of W depends upon the covariance matrix sigma, because the expression is sigma inverse mu I minus mu j. X naught, as before, if I assume P omega I and P omega j to be equal, that is the classes to be equally a priori, in that case sigma naught as before becomes half of mu I plus mu j. Okay. So, this expression simply becomes again my decision surface, the decision boundary between the classes omega I and omega j is orthogonal to W, but unlike in the previous case, it is not orthogonal to the line joining mu I and mu j. Right. So, it is orthogonal to W, but under the situation that P omega I and P omega j will to be equal, the line becomes a bisector of the line, the decision surface becomes a bisector of the line joining mu I and mu j, because when p omega I and p omega j they are equal, x naught is half of mu I plus mu j. So, it is halfway between mu I and mu j. So, my decision surface is a bisector of the line joining mu I and mu j, but it may not be an orthogonal bisector, because W is no longer in the direction of the line joining mu I and mu j in general. So, let us see that what will be the nature of the decision surface in this particular case. So, again for that I take a number of examples, number of feature vectors from class omega 1 and from class omega 2. So, in this case the feature vectors that I am taking from class omega 1 are all these feature vectors which are marked in blue. So, these are the feature vectors that I am taking from class omega 1, which are 6, 2, 9, 3, 7, 5 and 10, 6. Similarly, all these feature vectors which are in red, they are taken from class omega 2. The feature vectors are 6, 11, 9, 12, 7, 14 and 10, 15. So, here you find that unlike in the previous case, where the set of feature vectors were spherically distributed, in this case they are elliptically distributed. They are not spherical distribution anymore. So, given these feature vectors, now let us see that how we can find out the decision surface. So, for these two sets of feature vectors, I compute the mean vectors mu 1 for class omega 1 and also I compute mu 2 for class omega 2. Again there is a mistake. The second one here, this mu 1, this actually should be mu 2. This is not mu 1, but it is mu 2. So, mu 1 is equal to 8, 4 and mu 2 is equal to 8, 13. They are the mean vectors of the feature vectors taken from class omega 1 and class omega 2. So, once I have this, then again as before, I can compute the covariance matrices. So, as we have computed in the previous lecture, in the same manner, if I compute the covariance matrix, you will find that the covariance matrix for both the classes omega 1 and omega 2 will be half into 5, 3, 3, 5. So, this is the covariance matrix that you get for both the classes omega 1 and omega 2. And so, this is a case where my off diagonal elements, they are not 0 anymore. So, unlike in the previous case where I had the covariance matrix which was completely a diagonal matrix and all the diagonal elements were equal, in this case I have off diagonal elements which are non-zero. So, that means the feature components, the different components are not statistically independent anymore. However, for both the classes I have the same covariance matrix, that is half 5, 3, 3, 5. So, this comes under the case sigma I is equal to sigma. So, once I have this covariance matrix, I can compute sigma inverse, that is the covariance matrix inverse, okay. And using this, as we have seen earlier, that I can compute the decision surface, and the decision surface is given by W transpose x minus x naught equal to 0, where W is sigma inverse mu 2 minus mu 1. And you remember the sigma inverse that you have computed was 1 by 8, 5 minus 3 minus 3, 5, and mu 2 minus mu 1 is nothing but 0, 1. Okay. So, I get W which is minus 3, 5. So, that simply says that W is in the direction of minus 3, 5. W will be in this particular direction. So, here you find that this dark green line, this line represents the direction of W. Okay. And given this, I can also compute what is x naught as x naught is given by minus half, x naught is given by half mu 1 plus mu 2 minus this. And under the situation, if I assume that p omega 1 and p omega 2 to be equal, log of p omega 1 upon p omega 2, that will be equal to 0. That means, this term will be cancelled, giving x naught to be half of mu 1 plus mu 2. So, that simply says that our decision boundary, which will be orthogonal to sigma inverse mu 2 minus mu 1 or mu 1 minus mu 2, and it will pass through the midpoint between mu 1 and mu 2. So, this dark blue line is the line joining mu 1 and mu 2. Dark green line is sigma inverse mu 1 and mu 1 minus mu 2, and this dotted red line is the line which is orthogonal to this dark green line, and it passes through x naught, where x naught is half of mu 1 plus mu 2. So, this is mu 1 and this is mu 2. Okay. So, here you find that the decision boundary in this case is also linear, but the decision boundary is no longer orthogonal to the line joining mu 1 and mu 2. So, this was our second case, where sigma I was equal to sigma. Now, let us consider that what will be the discriminant function and the decision boundary in the most general case, where I have sigma I to be the most general one, that is, for different classes I can have different sigma y. It is possible that for some of the classes the sigma I will be orthogonal, but some other classes sigma I can be diagonal, but for some other classes it may not be diagonal. So, every class or the sample vectors taken from every class, they have their own covariance matrix sigma I. So, to see that what will be the nature of the discriminant function in such case, let us go back to the original g I x, where we have seen that g I x was minus d by 2 log of 2 pi minus half log of determinant sigma I minus half x minus mu I transpose sigma I inverse x minus mu I plus log of p omega I. So, here you find that as before, I can remove this term from g I x, because this is same for all values of I, whereas in the earlier cases we had ignored this term as well, half log determinant sigma I, because sigma I was same for all the classes. Now, sigma I is not same for all the classes, it is different for different classes. So, I cannot ignore this term anymore. So, that gives me that g I x will be simply minus half x minus mu I transpose sigma inverse x minus mu I plus log of p of omega I minus d by 2 log of mod of determinant sigma I. Right. So, given this, you find that this expression is of the form x transpose a I x plus b I transpose x plus c I. I can simplify this expression in this form: x transpose a I x plus b I transpose x plus c I. And now, we find that because of the presence of the term x transpose x, I will have, if the components are x 1, x 2, x 3 and so on of the feature vector x, I will have terms x 1 square, I will have terms x 2 square, I will have term x 3 square, I will have term x 1 into x 2, x 1 into x 3, x 2 into x 3, x 2 into x 5 and so on. So, that leads to a situation that the discriminant function g I x does not remain linear anymore, but it becomes a quadratic discriminant function because of the presence of quadratic terms. And over here this a I, it will be simply minus half sigma I inverse, and b I will be sigma I inverse mu I, and c I will be minus half mu I transpose sigma I inverse mu I minus half log of p of omega I plus this is minus half log of determinant sigma I plus log of p of omega I. So, C I will be minus half mu I transpose sigma inverse mu I minus half log of determinant sigma I plus log of p of omega I. So, my discriminant function becomes a nonlinear or quadratic discriminant function. And when I have such nonlinear discriminant functions, to find out the decision boundary between two classes omega I and omega j, now it is difficult to simplify as we have done in the previous case, unlike in the previous case. So, now what I have to do is I have to find out what is g I x, which will be, as we have seen, it will be x transpose a I x plus b I transpose x plus c I. Similarly, I have to compute what is g j x, which will be x transpose a j x plus b j transpose x plus c j, and to compute g x, which is the decision boundary between the two classes, I have to compute g j x, which is nothing but g I x minus g j x, and I have to equate this to equal to 0. So, whatever expression I get, that will be the decision boundary between the classes omega I and omega j. So, now let us see what will be the decision boundary in this kind of scenario. So, for this again I take a set of feature vectors. So, a set of feature vectors say 9, 10, 9, 14, 7, 12 and 11, 12, which are taken from class omega 2, that is this one, and I have a set of feature vectors 5, 4, 9, 2, 9, 6 and 13, 6, which are taken from class omega 1, and the feature vectors belonging to class omega 1 are these ones, right. So, as before, as we have done before, given these feature vectors, I can compute what is mu 1 and what is mu 2, that is the mean of feature vectors taken from class omega 1 and mean of feature vectors taken from class omega 2. And I can also compute the covariance matrix sigma 1 and sigma 2 for these two different classes. So, over here my mu 1, that is the mean of the feature vectors from class omega 1 will be 12, 6 and mu 2 will be 9, 4, and the covariance matrix sigma 1 is 2, 0, 0, 2. So, you find that this 2, 0, 0, 2 is the covariance matrix for these feature vectors. I think as we have doing earlier, this sigma 2 sigma 1 should actually be sigma 2. Anyway, that does not matter much. And for the other class, your sigma or the covariance matrix is 8 0 0 2, which is the covariance matrix over here, right. So, you find that in the first case, in this case the points are spherically distributed, and here the covariance matrix is of the form 2 0 0 2, which is nothing but of the form sigma square I. So, the points are spherically distributed, whereas in the second case, where my covariance matrix sigma 2 is 8 0 0 2, it is elliptically distributed, and because the variance of the component x 1 component is more than the variance of the x 2 component. So, obviously, the spread in x 1 direction is more than the spread in x 2 direction, and that makes it elliptical. So, given these two set of feature points, feature vectors, now as I find that the covariance matrix for the two classes are different. So, my discriminant function for the two classes, for the second class where covariance matrix is 8 0 0 2 will be a quadratic one, whereas the discriminant function for the first case where sigma 1, that is this one, because it is of the form sigma square I, the discriminant function for this class will be linear. So, over here my discriminant function will be quadratic, for this the discriminant function will be linear. So, to find out the decision surface between the two classes over here, I simply have to make g I x minus g j x and equate that to 0. And after equating that to 0, whatever I get, that becomes the decision surface. So, you find that as we have done before, that this is the expression of the covariance of the discriminant function, where the covariance matrix is not of the form I square I, right, and the discriminant function is a quadratic discriminant function. And given this particular situation, if I try to find out that what will be the decision boundary between the two classes. So, as we said that for this set of points, the discriminant function will be linear one. For this set of points, the discriminant function will be a quadratic one. And if I call it say g 1 x and if I call it g 2 x, the discriminant functions, the equation of the boundary will be given by g 1 x minus g 2 x, that will be equal to 0. And if you plot the decision boundary, you will find that the decision boundary will have a shape something like this, which is not a linear decision boundary anymore that we have obtained earlier, but in this case the decision boundary will be a nonlinear decision boundary or a quadratic decision boundary. Well, so with this I come to the end of this lecture. So, in this lecture and the previous two lectures, what we have tried to do is, we have tried to find out the discriminant functions of different classes, assuming that the distribution of points is multivariate normal distribution. And there we have taken three different cases. In the first case, we have assumed that the covariance matrices for all the classes are same and they are of the form sigma square I, and which case we have obtained the discriminant functions to be linear, and not only that, the decision boundary between the different classes, they are also linear. And under the situation when the a priori probabilities are same, we have seen that decision boundary is orthogonal bisector of the line joining mu 1 and mu 2. In the second case, we have assumed that the covariance matrices for different classes are same, but they may not be of simple form sigma square I. In that case also, the discriminant functions we have found to be linear, decision boundary was also linear, decision boundary was a bisector of the line joining mu 1 and mu 2 under the situation when a priori probabilities are same, but the decision boundary in general was not orthogonal to the line joining mu 1 and mu 2 because of the presence of the term sigma inverse. So, the direction of the decision boundary in that case depends upon the covariance matrix. And the third case was the more general case, where we assumed that the covariance matrix of all the classes are different, and in which case we have found that the discriminant function is not linear anymore. The discriminant function is a quadratic discriminant function, and given such quadratic distribution, the decision boundary to be the discriminant function to be a quadratic one. Using that, if I try to find out the separating boundary between the two classes, the separating boundary in general is quadratic. It is not linear anymore. I will stop here today. Thank you very much.